Good morning, ladies and gentlemen. Welcome to this lovely, chilly, rainy August day. Well, for me at least, that's when I'm filming. Today, we're going to be doing our first really long video, so make sure you have a cup of tea and are ready to rock. Today, we are going to be looking at impulse. This is a super important concept in the unit, and we're going to be coming back to it again and again and again. So, pay attention, have your notes, take your notes, write stuff down, pause the video as you need to write stuff down. It'll be grand. And let's jump right in. So, ladies and gentlemen, when an object is going to accelerate, now remember when we say accelerate, we can mean like positive acceleration or negative acceleration. So, speeding up or slowing down both means accelerate. So, our velocity is going to change. And remember that P is equal to mv for our momentum. Well, if our velocity is going to change, its momentum is going to change as well. So a change in momentum is defined as impulse. So this little bit here is not on your data sheet. Okay, you need to know that impulse is equal to delta P. Remember from Physics 20 that delta means change in. Okay, so remember that when you have a delta, it's going to mean momentum. So delta P is momentum final minus momentum initial. That isn't on your data sheet. By the time we get to Physics 30, I do make the assumption that you guys are comfortable with deltas, what delta means, and the ability to say delta P and just break it into PF minus PI. So that is an assumption that I make. Okay, guys? Okay. So let's think about changing our velocity. What does change in velocity actually mean? Acceleration. Because if we're going to have acceleration or velocity changing over time, we're going to get acceleration. Well, in order to accelerate, we need a net force. Bring back Newton's second law. So it's going to be, and remember, when a net force is going to act on an object over a period time, we get acceleration, right? So from your data sheet, which you can find this equation here, okay, our acceleration is equal to our force over mass, or F net equals ma. Okay, so where does this link us with impulse? But if an object is going to be accelerating and having an object or having a force acting on that object, it's going to experience impulse. Okay? So when you apply a net force to an object, it's going to accelerate, which is going to give it impulse. Yeah. So we can define acceleration not only as F over M, but we can define acceleration as delta V over time, right? So let us do a bit of lovely equation substitution. If in our F net equals ma, I am going to take this chunk here and replace the acceleration with delta V over delta T. Okay, so this A becomes this, delta V over delta T. We get this equation here. So the net force is going to equal your mass times delta V over time. When we multiply time over, we wind up with this equation. Force times time is equal to mass times delta V. That is your equation for impulse. All right? So this equation, ladies and gentlemen, is on your data sheet. Okay, so you don't need to memorize all of the substitution of equations and then how we derive this guy here. But I always find it good to know where, if we have that data, where can we get these equations from? Why does it make sense in the physics? So you can find that equation right here, okay, right there on your data sheet, right underneath your momentum equation. Cool beans? All right. So, ladies and gentlemen, force is in newtons, time is in seconds, mass is in kilograms, delta V is the change in velocity. So, ladies and gentlemen, what does that actually tell us? That our delta V is equal to VF minus V high. Okay, so that is going to play a role in your equations. Delta means change in. The deltas become very, very important, okay? All right, so let us rewrite this particular equation. Impulse is equal to force times time, so this half is impulse, and impulse is also equal to m delta v. So these other half equations aren't on the data sheet. However, there are going to be scenarios where you will just need force times time. There are going to be other scenarios where you'll need just mass times delta V. All right? So this half is impulse. This half is impulse. Okay? That's vital. We're going to be talking a lot more about the consequences of force times time on everything that we can think of, from vehicle collisions to rock climbing and the type of rope you use to eggs being dropped on pillows, right? So I even have a couple of YouTube videos in the Google Classroom section about how superheroes blatantly disregard impulse. It's not nice of them at all. So have a watch of those. They're awesome. So the two YouTube videos I want you to watch are by a channel called Because Science, and the host goes through how superheroes are saving us wrong by disregarding impulse and squashing us to death if the movies didn't make cool scenes, and why the superhero landing will actually break your legs. So give those a watch. They're awesome. He walks through the math of it, and you see these equations popping up quite a bit. It's pretty awesome. All right. So, and if we're in class, I'll have shown at least one of those videos in class. So they're fun. They're fun. So a couple other things about impulse. They've got the same units as momentum. So kilogram meters per second or Newton seconds. It is a vector, ladies and gentlemen. So because it's a vector, what do I want in vector questions? Direction. Now this bit here is super, super vital. Lots of stars kind of gives you an inclination that it's important. So if an object is going to be accelerating, okay, so have positive acceleration, speeding up, its impulse is going to be in the same direction as your initial velocity, okay? So if your initial velocity is positive and you're going faster, your impulse is going to be also in a positive direction. If an object is decelerating, which means negative velocity, that means impulse is going to be in the opposite direction. Okay, so if you were going to be slowing down, okay, that means if you have a positive initial velocity, your impulse is going to be in the same direction of your acceleration, which is going to be negative. All right? Okay, so that's a good way to think about it. You could think about the impulse being in the same direction as your acceleration, or the same direction as your net force, because they're linked. It's epic, right? Epic? All the way, guys. All the way. Okay, so, ladies and gentlemen, let us talk about a force versus time graph. Now, these graphs are going to be the most common type of graph that you're going to be seeing with impulse, okay? So, once again, force versus time. Title your graph. Force is 0 here, and this is going to be our force. Units in newtons. And this is going to be time in seconds. Now, ladies and gentlemen, what does it mean when we have positive and negative force? Direction of the force. Okay. So let's have a look at this. We're going to start with force being applied constantly over time. And then we're going to be having that. That's the graph pattern we're going to be analyzing. So let's talk about each of these pieces. So pause the video, draw that graph, and then we'll come back and keep adding stuff. All right. So, ladies and gentlemen, oh my god, this other pop-up showing up. And the school's got this weird artist school program thing. It keeps popping up on my screen and interrupting my videos. Yeah, it's not fun. Okay. I don't even know if you guys can see it or not when it pops up when it's filming. All right. So, ladies and gentlemen, let's start labeling these things. Now, as always, we always like to break our graphs down into their appropriate shapes. So this area up here, this is going to be an area of positive impulse. And my phone is ringing. I'm going to pause the video, see who's calling, and I will be right back. All right, sorry about that. We're back. So, ladies and gentlemen, this area is going to be a positive section of impulse. So, impulse causing acceleration. How do we know? Because the force is positive. If the force is going to be positive, that means it's going to be going in a positive direction. And if the net force is going in a positive direction, that means we are going to be accelerating and going faster. That means positive impulse. Positive acceleration, positive impulse. This guy down here is going to be negative impulse. Why is that? Because the force is going in a negative direction. If the force is going in a negative direction, it means our acceleration is going in a negative direction. It means we're slowing down. That means our impulse is going to be in a negative direction. Sounds good? Okay. So let us look at a couple of different things. What math can we use on this graph? Well, let's look at mathematically what the slope is going to mean. Remember, slope is equal to delta y over delta x. And, well, we've got force and time. So it would be change in force over change in time. Well, force divided by time doesn't mean anything, right? So that's not helpful to us. So the slope means nothing. So you cannot calculate slope off of this graph. It's not going to give you anything that is going to be in any way useful. However, let us look at what the area could mean on this graph. Force times time. Well, the area is equal to length times width when it comes to this, or area is going to equal base times height divided by 2 for this portion here for your triangle. Well, let's look at this guy here. Well, length times width, which would be this force here, times this times here. Well, area is going to equal force times your time, which, ladies and gentlemen, equals your impulse. Okay? So our area equals impulse. Okay? So that is going to be something that is going to come up. I'm pretty certain I give at least one question like this on either your quiz or unit test. I can't remember which one. Maybe both. I don't know. I can't remember what I've made at this point. I've been making so much physics stuff. I just can't keep up what I've even made at this point. All right. So, ladies and gentlemen, that is some important data there. I also want to talk a little bit about some of the different types of things you could see in graphs that absolutely show up on exams. I know that one for a fact, and it shows up on diploma questions too. Which, by the way, all of your unit tests and quizzes are made with old diploma questions, and a lot of your assignments too. You guys are going to be so ready for this diploma, it's not even funny. Okay, so this is another force versus time graph. So this is your force in newtons, and this is your time in seconds. So I'm going to draw two different colored lines here. Now, On our next example, we are going to be looking at dropping something on a hard surface, that's an egg, and versus dropping an egg on a soft surface. So what we are going to do is we are going to look at the amount of time that it is going to occur. So I've got another phone call here. Beg pardon for pausing again in the middle of a lesson. And we're back. So, ladies and gentlemen, what we're going to do is we are going to take a look at our next page first, and then we're going to come back and fill in this graph about our dropping eggs on a hard surface versus dropping eggs on a small surface. So then that way we have all of our graphs in kind of one little area, and then our notes and details in another little area. Okay? Alrighty-o. So, sorry, I'm running two computers. I got one over here, and I got all the work I've done previously on that one. So I'm really super techie today, with these YouTube videos. It's absolutely nuts. Like me running two computers simultaneously and the Wacom writing tablets. My home office has become like a little recording studio since March. All right. So, ladies and gentlemen, so let us look at our egg dropping and discuss impulse and force and time. And then what we are going to do is we're going to go back up and fill in these graphs. So, erase that random Newton there. So what we've got is we've got a couple of eggs. Okay, you see these eggs? They're being dropped from the same height, and we're going to assume these eggs are identical. Okay, when identical eggs are going to be dropped from the same height, that means they're going to have the same potential energy, and that means right before they hit the ground, they're going to have the exact same velocity. They're going to then come to a stop once they hit the ground. That means that they are going to have equal impulse, okay? These eggs are going to have equal impulse. So let's write this down. So same egg, therefore, same mass, therefore, oops, not therefore, oopsie, okay. We are going to have both of them are going to be dropped with the same VI. And because we're assuming they're on the same planet, because we have to say it, we can say, therefore, they are going to have the same VF, okay, before they hit the ground. Okay. Now, ladies and gentlemen, they are then going to come to a stop. Once they come to a stop, well, then their final VS during the time of in contact with that ground is also going to be the same. So that means that they are going to have, as they stop, they are going to experience the same impulse as they hit the surface. Okay, so because in the time that they are in contact with that ground, they're going to have the same velocity, like a millisecond, right when they touch the ground, they're going to have that same velocity. However, we have got two, and then eventually they're going to stop. Okay, that, and then so therefore their VF is going to be 0 when they're in contact with that. Okay, so we have a hard surface and a soft surface. When we have a hard surface and a soft surface with these eggs, let's think for a sec. Okay, they have the same impulse. They have the same delta P is going to equal the M delta V. However, when we drop an egg on a hard surface and we drop an egg on a soft surface, the results are different. The hard surface or egg smashes. Well, what is different between them? Time and the force, ladies and gentlemen. May the force be with you. So, ladies and gentlemen, what we've got is if m delta v, that's a upside down delta, not helpful. So m delta v is equal to force times time. Now, when an object is going to hit a hard surface, the time in which it stops is fast. It's immediate. Egg falls and splat. It's busted because the force is large, because time is small. Okay? So you're going to have a large force and a tiny delta tiny change in time. Okay? So this bit here is equal for both eggs. All right? So equal impulse. However, we can have a larger force in a smaller time. Okay? So this egg is going to come to a stop very quickly. Okay? This guy here, this large force, is what breaks the egg. Okay? So that egg is going to experience a big force because it gets its impulse all at once. Okay? Small time. Okay. Now when we drop an egg onto a pillow or onto a nice soft surface, think about the amount of time it takes for that egg to slow down. As soon as it hits that pillow, it's going to start hitting the ground slowly. Okay? It's going to stop. But we're taking more time in which to do so. So if we take more time in which to stop, then that means we're going to have, once again, the same m delta v. This is going to be the same for both eggs. Okay? Well, actually, same for both egglings. Excellent. All right. But because we are on a soft, squishy surface, we are increasing that time. We got big time, lots of time. We got lots of time for this topic. 2 puns, 1 breath. It's all good. So we are going to have, because that big change in time, we're going to have a little tiny force. Okay? So what happens? The egg stops slowly. Okay? So, because it's stopping slowly, it experiences less force. So I'll say the egg experiences less force, and so therefore it doesn't break. So this whole concept applies to a ton of stuff. So we use it in so much technology. It's crazy. So let's think for a moment. Airbags in your car. That's actually a super classic diploma exam topic, by the way. Crash test dummies, airbags, crumple zones. All of these safety pieces in the car absorb the energy, absorb that. They make more time. The car is still going to experience the same impulse when you run into a post as if you're driving one of those really, really old cars that, like, bam, run into a post and nothing happens. Well, the car's going to stop very suddenly. Okay? Whereas if in a more modern vehicle, the vehicle itself is going to crunch, and then the airbags are going to go off. It's buying you time. And you want to buy time when you are in a vehicle collision. Because what happens? You slow down more slowly. It takes more time. So therefore, you, the egg, don't squash. Okay? You don't want to squash. It's the same concept with things like helmets. Wear a helmet when you are biking or quadding or dirt biking or whatever you do. Okay? If it's a helmet-based sport, wear a helmet. Because what the helmet does is the helmet has got that hard, tough shell on the outside and the softer foam on the inside. When your head going to hit that foam, it's going to take more time to slow your head down to a stop. The impulse your brain experiences is going to be the same, but the force it experiences is going to be less. So therefore, and then if you were like hitting face on pavement, right? So you don't want your brain smeared all over the sidewalk. You don't want your brain experiencing the maximum force in the less amount of time. No, wear a helmet. Okay. Other things as well. I used to do a ton of rock climbing when I was younger. And back before the Crohn's disease and before I wound up being one bundle of like abdominal and hand pain. So can't climb anymore. It's so upsetting. Anyway, back when I did a ton of rock climbing when I was younger, we have two types of ropes that we're always asked about when you're doing the training courses. Well, what rope do you use? A static rope, which means a stiff rope. Okay, when you pull on it, it doesn't move. Or an elastic rope. When you pull on it, it's a bit stretchy. Well, what rope do you want? The stretchy rope. And it's entirely based on this equation. As when you're rock climbing, especially when you're lead climbing and you fall, you can be falling for quite a while before the rope catches you. So if you're falling for quite a while, and trust me, when you fall a good distance, it's fast. 1 minute, you're holding on the wall, and when you let go, and boom, you're at the end of the rope. So, and even with an elastic rope, man, it hurts, and bam, you're smashing into the rock face. Anyway, so if you had a static rope, when you fall and you have the harness that's around your waist, and bam, if that force is applied all at once, it will liquefy your gizzards. No, I'm exaggerating, but it will cause internal bleeding, and you can bleed to death because of the force your guts experience. That's bad. Guts are delicate. You don't want to put a bunch of force on them. Whereas if you have an elastic rope, you are going to fall farther, but you're going to buy more time. The rope is going to stretch, and it's going to slow you down slowly, so the force you experience is less, and you don't get internal bleeding. So we could go on with this all day, like the applications of the technology that we use with this piece of knowledge. Ain't physics grand? Protecting guts one day at a time. Okay, so ladies and gentlemen, let's look at some math with this. So when we look at our equation, we can have a look at, so when we look at m delta v is equal to force times time. Well, let's look at the relationship between force of time and give it a mathematical definition. What would you define it as? If you said inversely proportionate, you're correct. You would remember seeing similar patterns like this in chemistry, where you have the two things on one side, okay? Charles' law, Boyle's law, what have you. So anyway, so I'm going to divide out time on both sides. Cancels. Force is equal to m delta v over t. Well, let's make this, that's supposed to be a v, I dropped my v there. So, well, let's make the delta v and the mass the same as we did in this scenario. And it's force and time that we're changing, so we're going to remove those, add our proportionate sign, and we are going to wind up with force inversely proportionate to time. Okay, so that's vital. So force and time, that should be an m, are inversely proportionate. There we go. Cool beans? Okay, so ladies and gentlemen, we're going to go back up to our graph now. So I want you to flip back to your previous page, and I want you to look at this graph here. I'm going to do this dark blue line is going to be the egg on a hard surface. Now, when we look at this, as the egg starts to touch the hard surface, it is going to, as it continues to be in contact with this hard surface, it's going to experience more force. And then after it's smashed to smithereens, it's going to experience less force. I am going to use this pink line in order to represent, I will actually label this. So this guy is egg on hard surface. Okay. Now I'm going to do pink, which is going to be an egg on the soft surface. So it's experiencing less force, but its time, the time in which it is experiencing it is less. Okay. So this is egg on soft surface. There we go. Okay. So when the graphs are actually done properly with the right numbers and whatever, you are going to have the area under this, area under the blue line between that and the x-axis, and the area under the pink line is going to be the same. Okay, so area under blue and pink is going to be the same. So what does that mean? What does the area under the line of the graph mean? Impulse. So even graphically, we can see that we are going to have the same impulse, that same change in momentum, but it's going to be experienced over more time. Cool beans? Cool beans. Okay, so I know this is a lot. This has been a very dense video so far. What I would do now is, if you haven't done so already, take a moment to go and watch those 2 YouTube videos that I have put in Google Classroom. By Because Science. So you'll have the why superheroes are saving us wrong and don't do the superhero landing. They're absolutely hilarious, and the physics is sound. They're fun. They go into stuff in a little bit more detail than we need to go into with and they use some equations that we don't use, but they're fun. It's a fun channel to begin with. And the guy plays Magic the Gathering as well. He does Magic the Gathering videos, which, as a fan and player of the game, makes an even better channel. Moving on. So we've already spent a decent amount of time discussing that particular topic on reducing human injury with airbags and helmets and what have you. Okay. So we've already talked about that. We are now going to move along to do the math. Okay, so what types of calculations are you going to be seeing? Now, let's think for a moment. We spent a ton of time here talking about the theory of this before we even got into the equations. Can you expect to see theory questions on this on your unit test, on your diploma, on your quiz, and on your assignment? Of course you can! You will! So be prepared to have theory questions based on this on your unit test, lessons at hand, and on your diploma. All right. So, ladies and gentlemen, a satellite has a mass of 172 kilograms. And as always, I'm going to list out what I have as I go. So then that way I'm not having to fuss with stuff. Okay. This is, if you guys don't do this, and start listing out the numbers you have down the side, before you even start calculating, I highly recommend you do it. I don't take off points if you don't do it, but I've been teaching science long enough that I can 100% say that those who do list their numbers down the side are less likely to get the question wrong than those who don't. Good. All right. And is initially traveling, so that means a VI of 2.35 times 10 to the 3 meters per second. To correct its orbit, a thruster is fired for 2.27 seconds. Okay, which changes the speed of the satellite to, all right, our new VF, 2.89 times 10 to the 3 meters per second. Calculate the magnitude, of the net force generated by the thrusters. Okay, well, magnitude, that means I don't want direction. Okay, so if I ever say in a question, calculate the magnitude of something, I don't want the direction. I may not even give you enough info to tell you the direction. And in here, I certainly did not give you enough info to get anything close to a direction. So, no direction. Don't give me one. I don't want one. Okay. I say magnitude is something. Don't give a direction. Okay. So, ladies and gentlemen, we have all of our, that V dropped down. That happens sometimes. It's kind of annoying. There we go. We have these things. We are trying to calculate our net force. Okay. Well, what equation are we going to use? On your data sheet, we are going to come up with our Ft is equal to m delta V. Okay. Oops. Well, we're going to be using this equation. And what are we going to do? We're trying to find force. We just divide out time. And our force is going to equal m delta V over time. Remember, delta V, Vf minus Vi. Well, that's all I have to do for this question. So I have everything else. I'm going to plunk in my numbers. So 172. And then we've got our 2.89 times 10 to the 3 meters per second minus 2.35 times 10 to the 3 meters per second. Divide the lot by the change in time, which is 2.27 seconds. It's going to give me a force, ladies and gentlemen. 40916.299 ... Okay. We now need to put this in the manner in which it's going to get you full points. Remember, I deduct half a point for incorrect units, half a point for incorrect sig digs, half a point if you don't have a direction when I need one. Okay? And if you give me a direction on this question, I'll take a half a point off for that too, because you can't get a direction for this question. So if you're giving a direction, you're making it up. Okay? And I can't give points for when you're making up stuff. Okay. So, I know, guys, it seems harsh, but that's the way physics is. Like, the details are so important. It's ridiculous. As we mentioned earlier, you get an error in your sig digs wrong as an engineer, you're gonna have a bridge collapse. So these details are kind of important. And heck, years ago there was this airplane that was flying from, I can't remember where, from like somewhere around either out of Manitoba or into Manitoba, and the units were wrong on filling it up with fuel. So the airplane needed to be filled up in gallons, and the meter that was the techs were using to fill up the fuel was saying liters, and they didn't check the units. They said, oh, well, this many gallons. Okay, fill it up until that number said, okay, that many. Well, the machine was in liters. Well, a gallon is 4 liters. So they had a quarter of the fuel in the plane that they needed. And this plane literally ran out of fuel in the midair, and the pilots had to coast it to this emergency landing because someone screwed up their units. So, like, lives hang in the balance in these details, guys. So that's why we're doing this. I had to get everyone in the habit that these things actually matter. All right, sig digs, units, no direction. So when you look at the question, I want 3 sig digs. So that means this is going to have to be in scientific notation. This 6 will round that up to a 2. So that's fine. It doesn't round that up. So you are going to have 4.09 times 10 to the power of 4 newtons. If you wanted, you could choose to convert that into kilonewtons, and that would be fine too. Alrighty-o. Sounds good? Cool beans. Alright. Next question, ladies and gentlemen. Okay. A 1 kilogram ball, so mass 1 kilogram, hits the floor, and I can't see that with the open with tab. There we go. Hits the floor with a velocity of 2 meters per second. Okay, that's where it's starting. Okay, if the ball bounces, so you gotta, I have to sneeze. I'm a very dramatic sneezer. You know that awkward time when you have to sneeze, you can't sneeze, and you're like making a face? Yeah, it's like, yes, pre-sneeze. Okay. So that would be 2 meters per second. If the ball bounces upward off the floor with a velocity of 1.6, so VF is equal to 1.6 meters per second. What is the ball's change in momentum? Okay, there is one piece that we need to do that I have not yet taken into account here. Can you guys see what possibly I might have missed here? Direction. I did not write down my direction for my VI and my VF. So, because here, I've got one of my dog's tennis balls here. So, if you guys can see the desk. You know what? We're just going to go full screen for this. There we go. We're full screen. Okay. So, back up the camera. Show the desk. Okay. Here is my dog's ball, right? Okay, guys? And then I'm going to drop the ball, and and it's going to hit the desk and it's going to bounce. So the ball is going down. It is then going to be in contact with the desk for a period of time, and then it is going to go up again. My initial velocity, ladies and gentlemen, is going down. Then the final velocity is going up. All right. So we've got a fairly decent change in velocity going on. Okay. So now we're going back. So not looking at my desktop. And we're going to go back to full screen. How do I go back to full screen? There we go. There we go. I'm back in the corner. So we now need to put some direction on here. Now that direction piece is super important. So once again, it doesn't matter which one you make positive and which one you make negative, as long as you're consistent and know what your positives and negatives mean. I am going, for the sake of this question, to choose to make down negative. I am going to choose to make up positive. If you want to go the other way and make down positive and up negative, you're welcome to. But it's just going to mean that you need to keep track of what your positives and negatives mean. And either way, you need to be doing that. So just be aware. Whenever you choose to be positive or whatever you choose to be negative, keep in mind what they mean. Okay? Okay. So, I'm trying to calculate what is the ball's change in momentum. Well, that means what is its impulse. Okay? So impulse is equal to the change in momentum. We know that the change in momentum is equal to m delta v. Okay? Well, this is fairly straightforward. The most important part about this particular question is the direction, which is what I really wanted to talk about. And as well, recognizing that change in momentum means impulse. So we have our mass, which is a 1 kilogram ball. And our delta V is going to be our VF minus VI. So 1.6 minus negative, so we could do like that, 1.6 minus your negative 2. Okay? All right. So, ladies and gentlemen, once you do the math and plunk all that in your calculator, we are going to wind up with a value of 3.6 kilogram meters per second. It is a positive number. Remember, ladies and gentlemen, what does the positive number mean with the impulse? For this question, it means up. So that means on sig digs, 3 sig digs, 2, 3, so it means I want 2 sig digs. So my impulse is 3.6 kilogram meters per second up. I know I've had this question before. If can you use just the positive signs and the negative signs in place of writing up afterwards in this case? I'm going to say no. All right, because on your diploma exam, you are going to be having things like up, okay, as a possible answer. So you'll have 4 answers to pick from on a multiple choice question, and 2 will be different. You'll have 2 different numbers and 2 different directions, and one would say be up and one would be down. So you need to be paying attention to what your sign numbers mean, okay? So that is going to be the important part. Watch what your signs mean when it comes to direction, because it's going to be hugely important. Okay, guys? Okay. All right, let's scroll on down. Oh, look, a graph question. Yay, your favorite. We love graphs. Graphs are awesome. I love graphs. When I was in university, I never took notes on a computer. I mean, when I started university, goodness, 14 years ago. And so everyone was taking notes in pen and paper when I started. But because I was, I did 5 years for my 2 degrees, by the time I finished, I was one of the older students. And so I was still taking notes on pen and paper when most people were typing on their laptops. And I never switched over because I could draw my graphs. Just quickly, boom, boom, 2 axes, label, draw the pattern, done. It was awesome. And graphs are amazing. They're going to be your life if you take science and math in university. Like, they're awesome. All right. So moving on. So we're going to be looking at our lovely graph. And we have been asked, calculate the magnitude of the impulse. So when I say magnitude, I want no direction. Okay, of the impulse to provide it to an arrow shot from a bow given the following graph. Okay, so we don't really care that it's from an arrow from a bow. That's not going to change our question, although archery is a ton of fun. Okay. All right, so let's look at our graph. Remember, ladies and gentlemen, that when we are going to be calculating stuff off of a graph directly, we have to be using area or slope. Well, remember what we discussed earlier, slope means nothing on this graph, so slope is irrelevant to us. We need area, force times time. Okay, so our impulse is equal to force times time, which means we want area. Well, if we want area of this graph, we are going to have to break our graph into 2 shapes. Because we've got this triangle here. Now, please, please forgive my inability to draw a proper straight line on this. You guys should absolutely be using a ruler. Okay. I'm going to be calling this section here area 1. So this red checked box is area 1. Okay. I am going to call this blue checked box area 2. Now, remembering from our last year stuff, your impulse is going to equal area 1 plus area 2. Okay. So let's talk about area 1. Now, ladies and gentlemen, if you say, oh, well, if that's easy, it's 80 times, I need to scroll down here. There you go. 80 times 30. All right, so we're just going to write that bottom corner there is 30. Now, oh yeah, 80 times 30, we're good. Well, no, because with our triangle is not 80 units, guys. Okay, our triangle is absolutely not 80 units. All right, so well, we have 80 to 44. Okay, so that means it is going to be 80 minus 44, which is going to give you 36 newtons. How I managed to write a 6 instead of an N is beyond me. So that is going to be 36. Now, can we just multiply by 30 and carry on? Nope. What have I not done that I need to do? Units. Units matter, guys. This is in milliseconds. You gotta convert the units. All right, you gotta convert them units. So, because we have our 30 milliseconds and we're going to be using it on both shapes, I'm just going to convert the 30 seconds. Okay, so make a note of that. You have to watch your units on your graph. So really, really pay attention. Units are super important, okay? So we're going to convert our units and we're going to go, so 30 milliseconds, do some lovely unit analysis because unit analysis is epic. It's going to be 10 to the negative 3 seconds divided by our 1 millisecond. Units cancel. And we're going to wind up with 3.0 times 10 to the power of negative 2 seconds. So that's the value we are going to use when we're calculating our area for our shapes. Cool beans? All right. So what we've got is our delta P is going to equal area 1 plus area 2. Area 1 is going to be 36 Do I have enough space here? Maybe. If I break this down into chunks, I'll have space. Yeah, I'm just gonna, sorry guys, I'm trying to figure out how to organize my page so you guys can actually read it properly. I'll have more space down here. I'm just gonna write out my stuff down here. So area total, A1 plus A2. Okay. So our area total, remember our length there is our 36 newtons, and we are going to be multiplying that by our time. So the bottom part of that triangle, which is our 3 times 10 to the negative 2. Now, because that area 1, that's a triangle, we can't just do length times width. We have to do base times height divided by 2. So you're going to need to divide that by 2. So that's the value of area 1. You're going to add that area 2. We can see area 2 nicely here. So we have, this is 40 because it goes 0 to 40. So our 40 newtons, and it's taking up the full bottom again, so that is 3 times 10 to the power of negative 2 seconds. Okay, so that's area 2. Once you add those together, we get 1.9. So, ladies and gentlemen, we're going to go back and we're going to look at this question and we're going to see what do we need for sig digs in units. Well, the question says magnitude, so that means no direction with your answer. And 2, 2, 2 sig digs, 2, 2, 2 sig digs. Do not use that 0 in your sig digs. 0 is an absolute value. It's okay. So I'm going to put 2 sig digs, and then we are going to put units, which is going to be Newton seconds. If you use kilogram meters per second, that's also fine. They mean the same thing. But because we are multiplying force times time, Newton seconds is just the more appropriate answer, or more appropriate units. I won't deduct if you use kilogram meters per second. That's fine. There. Alrighty. So we could even write this out properly with our delta P is 1.9 Newton seconds. So. All right, guys. All right. Okay, doke. So what we've got, ladies and gentlemen, are practice problems for you guys to do. We've got these pages. These are the acceptable, intermediate, and excellence questions. I recommend doing a bunch of these questions. If you want to jump ahead to try the intermediate and excellence questions, go ahead. If you're finding this stuff, you're super comfortable with all this, you're good. But definitely spend some time with this. Do your practice problems. And then you can go do the necessary questions on your assignment. Those I'll post on Google Classroom. Okay. Watch those 2 YouTube videos if you haven't done so already. Those superhero videos, they're super fun. Get it? Super fun. Yeah. And they're nice and informative as well with the physics. All right. I hope you guys have a good day and no fires, injuries, explosions. Stay away from rampaging viruses. And we'll see you next time.